All right, thanks very much. So I want to start by thanking the organizers for putting together this great meeting. I'm looking forward to the week. Um, uh, a couple comments before I get started. First of all, it'd be great if some people left their videos on, because otherwise I'm going to feel like I'm talking to myself, even though you were instructed not to leave them on.
That's right.
Thank you. And the other thing is, so we have an hour and 15 minutes, but there's not a particular set of things that I need to cover here, and I think it'd be fun if we have questions and discussion. If that's okay with the organizers, we can do that during the talk. So my
Definitely.
assignment was negative cosmological constant, ADS, but I'm going to interpret that liberally. The topic is going to be wormholes in black holes and cosmology, and I'm going to talk about various kinds of wormholes. A lot of these are best understood in ADS and in ADS CFT, but don't necessarily require negative CC. So we're just going to talk about all different kinds of wormholes and how they apply in various cases. Okay, so I am going to talk about, this is just a broad overview of wormholes, and I'm not going to have references very much throughout the slides, but this is work by many, many people on this topic. Here's an incomplete list just to give you something to look at if you're looking at the video or the slides later. So I'll begin with some words of introduction. So we're used to thinking about a single copy of a black hole and the quantum information associated to a single copy of a black hole. And with a single copy, we can calculate the entropy of the black hole, of course, is area over 4. This is something we can calculate in the low energy theory. This is a coarse-grained density of states. Okay, so e to the s of the black hole, we usually think of this as a microcanonical entropy. This is coarse-grained in some way. I'm going to write that coarse graining as this. So that's these double angle brackets, refers to some sort of coarse graining. Of course, the true spectrum is presumably discrete, and especially in ADS, that is, the true spectrum of the black hole is a sum of delta functions, maybe with degeneracies, but generically not. Generically, without any symmetries to justify degeneracies, there won't be any. There's just be a long list of energy eigenvalues. More recently, it's been understood that with 2 copies of the black hole, we can make a wormhole. The simplest wormholes that we can talk about, and the ones I'll start with, are the double black hole wormholes, where you have essentially 2 copies of the partition function corresponding to these asymptotic regions. I'll have a lot more to say about this as we go, but for now, I'll just say that this apparently calculates microscopic correlations in the density of states. Okay, so from a single copy of the black hole, we learned about the smeared density of states. From 2 copies of the black hole, we apparently learn about correlations in the density of states. And this is something that's happening all in the low energy theory, apparently. So we can calculate these correlations using the low energy theory of gravity. A related story applies to correlations in the Hawking radiation, where if you consider multiple copies, you can learn some more detailed information about those correlations. But wait a minute, of course, if we're talking about quantum mechanics, then the product of the partition function like this, z times z, is just a product of 2 numbers. And obviously, the product of z and z cannot have more information than z itself. This just obviously has to factorize in quantum mechanics. So this is referred to as the factorization puzzle. Sometimes it's called a paradox. I don't think it's really a paradox, and that'll be part of the theme as I go along, is how to interpret these non-factorizing contributions without getting too exotic about it. So the question that this really raises, and one that we're going to have to address, is what do these angle brackets mean? So when we calculate black hole observables, especially these higher topology sort of new contributions that we're not so used to, what is it we're really calculating? What are these angle brackets that are responsible for these correlations? And there are various options. So briefly, I think there are roughly three interpretations. One is that this is an average, an explicit average of some kind. That is, that we're calculating a disorder average or an ensemble average over quantum theories. A second possibility is, sounds more exotic. The second possibility is that this is a effective decoherence into baby universes. This goes back to old ideas of Coleman and Giddings and Strominger, and more recently, Marloff and Maxfield. I would really, I won't have a whole lot to say about baby universes in this talk, but I would describe this as a bulk interpretation of number one. Okay, so the baby universe picture is a way of taking a disorder or ensemble average and interpreting it in terms of the gravitational path integral or in terms of the bulk theory. The third option, which really is distinct, is that these angle brackets are some sort of low energy coarse graining. That is, we're really doing quantum mechanics, but we're working in some approximation, and the angle brackets are somehow capturing that approximation that's relevant at low energies. In order to...
Can I ask a question since you allowed us to interrupt?
Please do.
So can a low energy observer living in this space-time distinguish 1, 2, or 3 with a low energy experiment, or are we doomed?
That's a great question. And I don't know the answer. I don't know the answer. I think that's kind of the crucial question in this business. Is we can interpret things these different ways, number 1 and 3, but it could be that the same low energy theory has these different interpretations, and that the correct one depends on the UV completion. We need to answer that question. It's a question of when we can trust the contributions to the path integral that I'm going to discuss. It's crucial. Thanks. Yeah. So I think all of these are viable. They're not mutually exclusive necessarily. There might be one interpretation in some theories and another interpretation in other theories. And as we go along and look at the various wormholes, I'm going to try to distinguish and say how they would be interpreted as disorder or how they would be interpreted as low energy coarse graining. And we sort of have that option. So we have to say which one we're talking about for each of these wormholes and see how it fits in. So when I talk about average dualities, let me sort of distinguish between these possibilities with some examples. When we talk about average dualities, we're talking about, for example, well, the original average duality is the duality between JT gravity in 2 dimensions and random matrix theory. The random matrix of this random matrix theory is to be viewed as a Hamiltonian of a 0+1 dimensional quantum system. So the randomness here is an ensemble average over theories. In higher dimensions, this duality works great in the sense that you can do calculations at all genus perturbatively. You can include non-perturbative effects, and you get a detailed matching between the two sides. In higher dimensions, the situation is less clear. So it's very natural to guess that three-dimensional pure gravity, that is just Einstein gravity alone, three-dimensional pure gravity involves an ensemble average. It's really the three-dimensional analog of JT gravity. And in work before this random matrix duality, there were a lot of puzzles in 3D gravity. In particular, it didn't seem to have a consistent partition function, the pure theory. And there are hints now that those puzzles are fixed by giving it an ensemble interpretation. So I think that's a really interesting direction. But it's still a mystery because we don't know what the dual is supposed to be. It seems to involve some averaging, but what is the dual? Is it an average CFT2? Well, I suppose so, but we have no idea what that is really.
Tom, can I?
Yeah.
Have a question? Yeah. Just to understand this average CFT story, just to get some hints about it. And since you mentioned that this is related to the fact of fixing some problems of pure gravity in 3 dimensions have, taking into account that one seemingly good idea to investigate how to solve this problem was related to polymorphic factorization of the partition function. So is this related to that or somehow?
Well, it's related to that story. I would say it's the continuation of that. So the quick version, let me give the quick like 14-year version briefly here. The outline is that Witten proposed a holomorphically factorizing partition function. Then Maloney and Witten did the calculation of the partition function and found that it did not holomorphically factorize. And furthermore, that it didn't seem to make sense as a quantum theory. There were two issues. First of all, the spectrum was continuous. And second of all, the spectrum was non-unitary. It was not positive. The density of states was not positive. The modern interpretation is that the continuous spectrum is not a problem. That continuous spectrum comes from averaging, or this is the averaging interpretation. I'm not saying this has been settled, but the averaging interpretation is that a continuous spectrum is perfectly fine. It comes from averaging over an ensemble. Now the issue of the non-unitary, the negativeness in the spectrum, there's a proposal that including higher topologies in the path integral could fix that problem. And there's some evidence for that that comes from reducing to JT gravity in a certain limit and seeing that it has the right effect to fix that problem with the negative density of states. That proposal hasn't been fully worked. It's a proposal. It hasn't been fully shown, but it seems that very well could work. The difficulty is that when Maloney and Witten did the calculation, they summed over saddles, and those can be classified and written down. And now we're talking about off-shell topologies, where it's very hard to imagine, or it's a very complicated problem to imagine summing over all 3 topologies, not just hyperbolic manifolds, but all 3 topologies, and somehow doing the path integral exactly on all those topologies. It just sounds like a terribly intimidating problem. So we don't know what an average CFT is. Maybe it can be defined microscopically, or maybe we have to think about it more in terms of, say, bootstrap data. That maybe we can think of it in terms, if we think about, for example, OPE coefficients, then it becomes possible to say what's meant by average. But exactly what this theory is, we don't know.
But it's allowed. Sorry, Tom. The average CFT is allowed to have a continuous spectrum.
Yeah, just because even if each individual CFT is discrete, the average can be continuous.
And a related question, there were recent proposals about a very stringy ADS3 CFT2 by Gabardiel and friends, and they had Louisville as part of their description. Now, those would seem to be holographic pairs to the extent that the tensionless limit makes sense, that have continuous spectra. But I wouldn't call those average CFTs, or would you?
No, I wouldn't call those average CFTs. Yeah, there's two ways that a CFT can have two reasonable ways that I know of for a CFT to have a continuous spectrum. One is for it to have a non-compact target space. So like the non-compact free boson has a continuous spectrum that goes down to 0. That's an individual CFT. It has a spectrum that goes down to 0, but the vacuum state is not normalizable because of this non-compactness. So in that case, so we can sort of tell the difference between these. If the vacuum state is normalizable and you have a continuous spectrum, then that looks more like an ensemble average. And that's actually what happened in the Maloney-Witten calculation, was that there was a vacuum state and then a continuum above it. Now, I don't know, maybe there's some other way for that to happen involving non-compactness, but I don't know of a way to do that. There's a toy model for this in 3 dimensions, in 3-dimensional gravity, which is this Narain duality. So the Narain duality is a toy model for an averaged holographic duality. It's not a theory of gravity. It's a theory where the bulk theory is an abelian Chern-Simons theory. So if you think of 3D gravity as being similar to SL2C Chern-Simons, then you have to imagine replacing that SL2C by a U1 to the n, by abelian Chern-Simons. And there's a duality between that theory summed over topologies and the ensemble average of the Narain CFT. That is just the ordinary toroidal compactification of n-free bosons, not interpreted as a world sheet theory, but as a boundary, as the boundary CFT dual. So this is a toy model, but the interesting thing here is that it's really there's really this correspondence between summing over topologies in the bulk, in the bulk path integral, and integrating over moduli in the dual CFT. These really seem to go hand in hand. And there's that also seems to be true in some of these other examples. If we go up above 3 dimensions, then we don't have any examples. And it wouldn't make any sense, really, to talk about the case of pure gravity in 4 dimensions. It's not normalizable. Of course, we can't really talk about pure Einstein gravity above 3 dimensions. But it's plausible, I think, that there's some effective field theory description along these lines. That is, that the effective field theory of low energy Einstein gravity very well could have a nice duality, approximate duality, a low energy duality to something involving some randomness. But we don't have an example like that. I think that's not known. So moving on to the other possibility of low energy coarse graining. So the way to think about this is that it's like nuclear physics. Okay, so nuclear physics has a relationship to random matrix theory. That it seems to give us random matrix theory seems to give us some things that agree with nuclear physics. But of course, that doesn't mean that we conclude that that quantum mechanics is wrong and nuclei are described by actual random matrices. It's just an approximation, one that works in chaotic theories. And it could be that this is also what we're seeing in black holes. And the examples where we think that's the case are, for example, the the classic ADS-CFT examples in string theory, where we don't think there's any kind of ensemble average going on over theories. But also, you can think of the SYK model with fixed couplings as belonging in this class. So if you take the SYK model, which has a relation to random matrix theory at low energies, if you take the SYK model and average over disorder, which is usually what we mean by the SYK model, then that gives something like a random matrix theory averaged over what's related to random matrix theory. But if you fix the couplings, then it's just one particular quantum theory. And so this is a case where you still might hope to learn something from random matrix theory, but the interpretation is different. Okay, you can still apply random matrix theory to an individual SYK model, but you have to interpret your observables and your results differently than you would if you were really doing the average. In fact, I think any low energy theory can be viewed this way, including JT gravity. If you think of JT gravity as defined by the path integral, then it's random matrix theory. That was the duality of Saad, Schenker, and Stanford. But if you think of taking JT gravity and coupling it to matter, then that path integral breaks down. And it's now just a low energy effective theory. And in that picture of JT gravity, we have to reinterpret. In that picture of JT gravity, it could be that it's UV completed by an individual quantum theory, and we need to interpret it that way. So the rough picture of low energy coarse graining, I think, is clear roughly what I mean by that. But how do you actually quantify this, and what are the tools we have for dealing with it? Well, I won't go into a lot of details, but one is the eigenstate thermalization hypothesis. And another is more recent is this effective field theory of the quantum ergodic limit discussed by these authors and others recently. So, well, I'm not going to go into that, but I just want to point out that we do have ways of really relating this to a low energy coarse graining. It's not just words. That you really can there are tools for doing these calculations in that language. Okay, so with that very lengthy introduction, I'm now going to go on and talk about some examples. And what I hope I've gotten across in this introduction is that the key question here that's really been raised by a lot of this work is, how much does the low energy theory know about the UV? It seems to know more than we thought. We knew that it could tell us the average density of states. Apparently, it can tell us the pair, something about the pair correlations. But how much really does it know? A plausible situation is that the low energy theory knows everything that's universal. Maybe it knows everything that's universal about the UV. But we don't know what that list is. We don't know what the universal observables are. So this is what we need to understand. There isn't a general answer. I think this is still unclear. We don't know the general answer to this question. This is what we're all trying to figure out. So what I'm going to do is just go through some examples of wormholes and tell you how they fit into this picture. And I'll be careful to try to talk about the disordered and the non-disordered interpretations, because in many cases you have both, as I've been stressing. So wormhole number one. The first wormhole is the one I drew before. It's the double black hole. Depending on dimensions, it's sometimes called the double trumpet, or the double torus, or there's a saddle called the double cone that I'll come to in a minute. These are all related to this double black hole. So what we're interested in calculating is the connected part of ZZ. The path integral boundary conditions for that are to have two circles, one of two Euclidean time circles, one of size beta 1 and one of size beta 2. Now, this is not a saddle. So these calculations can be done in various cases, but this is never a cell, as far as I know. Which means that we can't just use our usual semi-classical approximation tricks. We have to actually do the path integral. At least naively, we have to actually do the path integral to study this contribution to ZZ. And what that path integral looks like, well, first I should say how it's done. So there's a technique to do this path integral, first in JT and more recently in 3D gravity and in higher dimensions. This has been worked out by Kotler and Jensen. The idea is that you fix something about this solution. For example, you can fix the length of the wormhole, or you can fix the size of the neck here. These are basically the same. Or you can think of this as fixing the energy at one of the ends. There's really you only have to fix one variable. These are just three ways of saying the same thing. Then with that fixed, you now get an action. I'm afraid I may have messed up the sign in this exponent here. So that's, I think, is a typo. But anyway, you get, once you fix that parameter, then you get an on-shell action, which is this term up here. And you get so to do the full path integral, we should also include the quantum effects around that action. And then we have to integrate over the parameter that we've fixed, the size of the throat or the energy or the length. And when you write this down, what you find is that this is dominated. No, I guess I had the sign right. Okay, because this should be dominated at low energies. And that's a limit where, so that's a limit where this throat here, the neck, is shrinking to 0 size. So this is a UV limit. It's dominated by the UV. So what are we supposed to do about that? Well, in JT gravity and in 3D pure gravity, this has been done. And you just have to do the path integral. You have to include that quantum effect and then do the integral. And you can do that in these simplified theories. And what's found is what's called the ramp. So this is a universal contribution to ZZ. And it's a contribution at imaginary temperatures. So we take the temperatures to be imaginary, IT and minus IT, take T to be large, and there's a piece in this integral that grows as T. If you take the Fourier transform of that ZZ, or Laplace transform, then you can reinterpret this as a correlation function of the energy eigenvalues, of the energy densities, and it gives you a term that looks like this. So this is interpreted as level repulsion in the quantum system, and agrees with the expectation of random matrix theory. Now, as I said, this calculation is UV sensitive. The only reason that it could be done in these theories is because we were talking about theories of pure gravity, JT or three-dimensional pure gravity. There's both theories of pure gravity, where you really think of the theory as defined by the path integral, the gravitational path integral. In non-disordered theories, like if we take 2B string theory, or if we take SYK and couple it to matter, this calculation cannot be done. However, it still seems to give the right answer. So in other words, it appears that there are very closely related observables that can be calculated reliably. So I'll be a little bit sketchy about this. The details are a little bit more complicated. For example, maybe you can't calculate ZZ because it's UV sensitive, but you can calculate some kind of coarse-grained version of ZZ. So for example, you could integrate it over time. You could average it over a time window. And even though this integrand is UV sensitive, the integral appears to be universal. So the right-hand side is not true so this equation is not true at the statement of the integrand because it's UV sensitive, but that washes out in the coarse graining over time and does appear to give you a reliable calculation of this late time spectral form factor. So the integral here is acting as the coarse graining. Remember, we started with the question, what are these angle brackets? What are we averaging over? In this case, time, and that projects out some UV contributions. If you do this integral carefully, then you can find a contribution which is called the double cone saddle point. The double cone again gives a linear in time spectral form factor, the ramp, and therefore seems to be telling you that level repulsion is a universal fact about gravity in the UV. Now, this isn't 100% satisfying because, well, it's universal if you believe the calculation. We included this. This contribution to the path integral, but we're not sure what the errors are. We don't know what the other contributions to the path integral are, and whether those could modify this result. So it's very intriguing. It seems to be giving this universal answer that makes a lot of sense. Level repulsion is generic, or expected to be generic in chaotic systems, but we don't know well enough how to control calculations like this. A related story. Yeah.
A question. Just going back to how you explained how to do this calculation. So you just said you fix the length of this trumpet, or like the B, right?
Yes, that's right.
So and then you just like do all the integrals over all of the things that have, because if you have a fixed length, can you not have different B?
And
the B is like the minimal one, right?
Yeah, it's there's a saddle. So the point is that once you fix the length, there's now a saddle point. Okay, so you
okay, good. So I missed that point. Okay, good. Thank you.
Yeah.
I missed that point. Thank you.
Yeah. So a related story is the story of late time 2-point functions. So famously, the thermal 2-point function at late times is a version of the information paradox. So this is Maldasena's information paradox in the eternal black hole. You take this late time 2-point function and calculate it in the black hole, then it decays exponentially to 0. And that's just not possible in a good quantum theory with a finite entropy. The relationship, and this was worked out in this paper, is that there are wormholes that look like the one drawn here, which give you the dominant contribution at late times. So what I'm drawing here is so this is the thermal circle. I'm drawing this for 2-dimensional gravity. This is the thermal circle. If we were just talking about the black hole contribution, this would be a disk. But what was argued is that once you add these handles, you have these wormhole contributions, and these can dominate at late times. So this is directly related to this issue of the double black hole. The reason for that is if I cut this, so let me cut up this path integral like this. And then you see this tube here is exactly the same tube that contributed to the double black hole. And when he does this calculation, what he finds is at late times, you basically get a convolution of two effects. You have the contribution from the spectral form factor, which is this tube. And then you have some second contribution from the operators O that you're calculating the 2-point function of. And so the late time 2-point function is some convolution of the effects of the pair correlations and the matrix elements of the operator themselves. And he showed that this convolution is exactly what you'd expect from a random matrix or eigenstate thermalization type analysis of this correlation function. Okay, let me now move on to wormhole number 2. So wormhole number 2 is a little different, but I want to talk about it because it sends an important message, and this is the Madison-Chi wormhole. Start with the two-dimensional double black hole. That is the double trumpet, this one we've been talking about. Cut it in half and put a boundary condition. So instead of thinking of this as ZZ, we're just going to take this, cut it in half, put a boundary condition on one end, and put on the other end, that defines a quantum state. Okay, so we think of this path integral here as preparing some quantum state. There's a boundary condition at the bottom, and the top here is the quantum state that we're preparing, which turns out to be essentially the thermal field double state. Now, take this state that we've created by this Euclidean path integral and continue to Lorentzian. What you get is global ADS2. So the continuation to Lorentzian of this geometry is just global ADS2. And they refer to this as an eternal traversable wormhole, just because, well, in ADS2 you can send stuff across and you can send it back, and so it really is like a traversable wormhole. Note that when we do ordinary ADS2 holography, you can't send stuff from one side to the other because you really have to describe it in the black hole coordinates where it's not traversable. But in this case, you get global ADS2. So far I've just described a quantum state. I haven't said anything about a duality, but what is the interpretation here? The interpretation is that this is the ground state of the gapped theory that you get by taking two copies of your quantum mechanics, one for each boundary of ADS2. So you have one on the left, you have one on the right. If you took these two copies without any coupling, they would just be dual to two copies of ADS2. But now you add this coupling, this double trace coupling between the two theories, and flow to the infrared. And in fact, they show that this very universally and generically gives you a ground state. In this theory is now gapped, but the ground state of this theory is very close to the thermal field double state of the original system and is dual to this ADS2. So what's happened is that the interactions glue the theories together in the infrared. This seems to be something that's special to ADS2. There's a topological censorship theorem that prevents you from having solutions like this in higher dimensional ADS. So this seems to be special to ADS2, but on the other hand, ADS2 is very generic in extremal black holes, so it's common in that sense.
What happens to is this supposed to be a picture that has one of these JT interpretations as well? What
Yeah,
happens
we can
to
yeah, you can do this in any quantum mechanics, but in particular, you can do it in JT in
and the
SYK.
bilaton grows in toward both boundaries in this case,
Yes, that's right.
but that violates the null energy condition. If there's a higher dimension interpretation, that would violate the null energy condition, wouldn't it?
By higher
It would be
dimensional,
like a sphere shrinking.
I think it's okay to violate it here. It's the two theories are coupled, and so like it's
but then
okay
your comment about higher dimensions is not particularly pertinent in the sense that if you're allowed to violate the null energy condition, you could imagine these kind of theorems, topological censorship theorems, to be evaded.
That's a good point. Yeah, that's a good point. It won't be, you can't do it with a vacuum solution like we did in 2 dimensions, but that doesn't prove that you can't do it at all.
Okay, thank you.
So what is the lesson here I wanted to emphasize? It's that often a wormhole that seems to be a tiny subleading effect, an unreliable subleading effect, can be made dominant and reliable by changing the question slightly. Okay, so remember we started with the double trumpet, which was a off-shell configuration. If we couple that theory to matter, we can't really make sense of the starting point of how I described this. The starting point was this double black hole, and that is not a saddle point. And if we couple it to matter, we don't know how to interpret it or whether it contributes to any reliable observable. But you have this wormhole and you'd like to use it for something. So what Maldacena and she did was to change the question a bit by adding these interactions and causing this to become the dominant saddle point as opposed to the disconnected one. And quite often that's the way to think about it, to think about these wormholes. You have some wormhole, you'd like to interpret it. At first it might look like some tiny effect. Well, your task is to figure out a way to change the question a little bit and make it dominant and trustworthy. Okay, so that's in this case done by triggering RG flow. There are various ways you might change the question. You might average over theories. You might average over something else like time, as we saw in the spectral form factor. You might trigger an RG flow like we just did. Or you might go to late times, which is what we're about to do in the discussion of Hawking radiation and the replica wormhole.
I have a question.
Yes.
So earlier when we fixed the solutions by fixing certain parameters of the solution, did that also have a interpretation as coupling the theories with any particular operators? Or did it, like, were those parameters fixed by at least deforming the action, or were they just by fiat imposed on the solutions?
Well, you can always, yeah, I guess you can always sort of view it either way. If you have some constraint like that, then you can, well, sorry, I take it back. It's a bulk constraint. So you can think of that bulk constraint by adding a Lagrange multiplier to the bulk action. But whether you can think of that as adding some interactions to the boundary theories, I don't know of any way of doing that.
For instance, like, we also had a solution where we fixed the energy, and that seemed like a thing you could completely do from the boundary, right? That too without coupling the theories. Like separately, you could fix the energy by adding some boundary.
Yeah, I agree. That sounds possible. Yeah, I agree that there might be another interpretation where you couple them. Yeah. I don't think you don't have to couple them though. We can just think of it as a Yeah, I guess maybe what you're saying is that when I discussed the double wormhole, I said that we can make it reliable by averaging over something else. Well, maybe there's something more like adding couplings that would also make it reliable. The interpretation might be a bit different, but I agree that that very well could be. Okay, just a brief interlude before wormhole number 3 is a few comments on hydrodynamics and eigenstate thermalization. I just want to be clear that this is not a very exotic point of view. I mean, the idea that gravity has both a averaged and a coarse and a low energy coarse graining interpretation, I don't think is exotic. I think exactly the same thing is true of hydrodynamics. That if you give me a fluid, I cannot tell if that fluid is an individual quantum mechanical theory, which has been coarse grained in terms of, because I'm measuring low energy observables, or whether somehow the universe itself is an ensemble, and my fluid is living in this ensemble universe. I can't tell the difference if you give me a glass of water. So I don't know if it's that different with gravity. To make this a little bit more formalized, the eigenstate thermalization hypothesis says that matrix elements of operators, I've taken one with a Z2 symmetry, so I can ignore the first term, but these matrix elements in a heavy eigenstate have a smooth piece, which is essentially just the square root of the thermal 2-point function. And then they have a random matrix piece. And since hydrodynamics, or at least linear response, so these 2-point functions are the theory of linear response. And so hydrodynamics is the theory of the smooth part. If we generalize a bit and just talk about the whole low energy theory, including correlation functions, then that'll also include some information about the statistics of these random matrices. But obviously it's not going to tell you about, obviously it won't tell you the actual entries of the matrix. And it's equally obvious that coarse graining the observables is necessary and is exactly the right way to eliminate the UV sensitivity. If I try to use hydrodynamics to calculate the location of this atom here, then I'm going to fail miserably. But if I try to use it to calculate some average properties of a bunch of atoms, then that's exactly what it's designed for. So this coarse graining is not necessarily something too exotic. This is really something that we're used to. You can think of it, you can think of hydrodynamics either as averaged over theories or as a low energy coarse graining.
Just a clarificational question. I appreciate the analogy, but is there an analog? Can you extend it to from the hydro side to what the Euclidean path integral of gravity is?
No, I think it's quite, what seems to be the case is that I don't mean to say that hydro knows as much about the UV as gravity. I don't mean to say that at all. I don't think that's true. What I mean is that, yeah, I think that gravity knows a lot more about the UV than hydro. And that's somehow what the path integral is giving us. But the fact that it's the role of averaging might be similar. That's all I'm saying. Yeah, thank you for pointing that out. I don't mean to say that gravity is just like hydro.
Sorry, Tom, can I follow up on that?
Sorry?
Can I follow up on that?
Yeah.
Do you know of any context where people have used, I don't know, like subleading saddles in hydro to try to probe something you didn't think you had access to, like the resummation of hydro or something like that?
No. I don't. Do you?
No, I don't. I'm just curious. I mean, we're saying that maybe it's different from gravity, but maybe we just haven't asked that question in hydro
I
yet.
think that's possible. I think that's possible. Yeah, we have to take a sort of generalized notion of hydro. You know, I don't think hydro knows about late time 2-point functions and the ramp, for example. So it's a bit more general than what we usually think of as hydrodynamics. But you could be right. That maybe if we thought about it right, it would be the same. This is, I would say, this is maybe the this is one way of describing what Julian and collaborators have been doing. Is writing down an effective theory that's smarter, that does sort of know as much as gravity does.
Thanks.
Okay, wormhole number 3 is the replica wormhole. So the replica wormhole we can think of as similar to what I've been describing, in that you know, if you have one copy of the black hole, you get information about the 1-point function. If you have more copies of the black hole, then you get more information about the correlations amongst the energy levels. But now we're not talking about the energy levels of the black hole. We're talking about the density matrix of the radiation. So I'll just describe this in terms of the purity. So if we think about the purity of a density matrix is the trace of rho squared. This is called the purity because if you get 1, then it means rho is a projection operator and therefore the state is pure. If you don't get 1, then the state is not pure. And if we take the density matrix rho r for Hawking radiation, is determined by well, it can be calculated in the path integral approach by a path integral on the evaporating black hole. So for 2 copies of rho r, we have 2 copies of the evaporating black hole. The regions r here are glued together by the matrix multiplication. And this blue region is the island, and the island involves a sort of wormhole bridge between the island is strictly there in the replica limit. But if we talk about the purity, then there's this wormhole here inside the black hole interior. And when you look at the late times of this path integral calculation, it's very easy to see that that this just becomes 1 at late times, or that it factorizes into the trace of rho squared, exactly because you've included the wormhole in the interior. So this is something you can convince yourself just by drawing the picture carefully in the late time limit. Now the full story of islands and replica wormholes is something more complicated and quantitative about the whole evaporation process and getting the page curve. But if you just want to ask about the late time limit, then drawing this picture is enough. It's enough to tell you that the purity is 1. And in fact, this picture was drawn years ago by Polchinski and Strominger for this reason. The replica wormhole sort of becomes the Polchinski-Strominger wormhole if you take the late time limit. The reason that the reason we don't usually describe it that way is that the late time limit is not controlled, because now this wormhole is hitting the black hole singularity, and we lose control there. There's Planck scale curvature, but you get the right intuition from drawing these pictures. So the Euclidean version of this replica wormhole looks something like this. We're calculating trace of rho squared. So there's 2 copies of the Euclidean space-time that are glued together along. This is a bridge that glues together the region R. And the point of the replica wormhole is that you can have these tubes that form connecting the 2 sheets, or the 2 copies the Euclidean black hole. And that those are necessary in order to get a reasonable late time purity or Renyi entropy or von Neumann entropy. But I don't want to talk about the page curve. I want to talk about how this fits into the other things that I've been discussing. So this wormhole does not have a factorization problem or puzzle or paradox. Now, the double black hole that contributes to the spectral form factor, that was a product of two numbers. Z of beta 1 is a number, Z of beta 2 is a number. Now we're not calculating something that factorizes. We're calculating trace of rho r squared. So it doesn't have to factorize. If you look at the picture, then the point is that these two theories are glued together along the bridge. So you've explicitly coupled the two copies of the black hole when you do this calculation. You've explicitly coupled them. There's no reason that they should give a factorizing answer. However, there are very similar wormholes discussed by Douglas Stanford, which do have a factorization problem. Okay, so this is a different calculation, but the same wormhole, essentially. The calculation now is a product of 2-point functions. We calculate a product of 2-point functions, one set of not 2-point functions, n-point functions. We have one here and another here. Then we can think of, let's insert those operators in a long row right along what used to be the bridge connecting the two wormholes. So we insert these operators along this line here, and we just take two copies of that. Well, those operator insertions produce a very similar stress energy, an indistinguishable stress energy as compared to the bridge that we drew earlier, and therefore can support this wormhole solution as well. It's essentially the same wormhole, but now contributing to an observable that was supposed to factorize. So strictly speaking, there was no puzzle in the replica wormhole, but it's hard to explain why you'd like to include this replica wormhole and why you would not like to include this almost identical saddle that contributes to the product of endpoint functions. Now, again, we have the option of interpreting this different ways. We can think of it in terms of a disordered theory, or we can think of it as a low energy coarse graining. So it very well could be that the puzzle is not necessarily a paradox. It's just that we need to interpret it in one of those ways. So you might reasonably ask a question at this point. So is the Hawking radiation pure or not? That's what replica wormholes and islands were supposed to tell us, is about whether the Hawking radiation is pure. The answer is unclear. Even if you accept the replica wormholes and the islands, the answer is unclear. It appears that we have these two options about how to interpret things. That if we interpret this as a disorder calculation, or the baby universe interpretation, then I would not say that Hawking radiation is pure in the regular sense. In other words, the density matrix, if you just have one copy of the black hole, and you only get to do the experiment once, and you create the black hole by deterministic collapse, and then you ask, do I know the density matrix of the radiation, and is it a pure state in a quantum theory? The answer is no. The Hawking radiation is not predictable, but there's some unitarity somehow in the ensemble sense, because if you do a calculation involving replicas, you do get 1 for the purity. And similarly, if you calculate the page curve by the replica method, you'll get the unitary page curve. But it's not exactly, I still wouldn't call that unitary evaporation, because it's not just ordinary quantum mechanics. So that's one option. Or you can take this low energy effective field theory interpretation, then the answer is yes. But it's not clear how to decide. And this is the point that Dio was asking about earlier. It's not, if you're just a low energy observer, it's not clear how you're supposed to decide, or whether it's even possible in principle to decide which of these scenarios you're in. Okay. I didn't even think I'd make it to the 4th wormhole, yet here we are. So we can talk about wormhole number 4, the Brockhead. But we can also pause and discuss if we want to. There's not a particular, like I said, there's not a particular set of things that we have to go through. So if there are questions, we could pause here for a minute.
I guess the real question is, in the answer, in the case that it's not quite unitary, there are different degrees of violations of unitarity, right? If you just have negative probabilities, strange things can happen at low energy. This seems to be a far more subtle form of violating unitarity, where in order to observe the absence of unitarity, you would need rather elaborate or ultraviolet sensitive observables somehow. It would be at the level of quantities which are non-averaging, and you would have to be able to measure those. And in order to measure those, you might need elaborate experimental apparatus. Can you elaborate on that a little? The role of self-averaging quantities. Yeah. Sorry, I've been out of the loop, so I don't know.
I agree with your comment. It's sort of right. It's a ensemble average of unitary theories. That's a lot of unitarity being built in. It's not that it's not just the information is lost. There's a lot of unitarity there, but it's not as unitary as well. I won't count it as actual unitary evaporation in the sense that like a black hole acts like a piece of coal when viewed from far away. Yeah. And how do we decide? It's a very
clever form of non-unitarity because it shields itself away from the low energy observer, right? That's why this was, going back to your Wigner nuclei, or the spin glass example as well, quantum spin glasses, for example, that was why it was such a remarkable tool, because they could use it to compute things effectively without spoiling everything. So I guess I'd like to see to what extent this can be quantified in the black hole context. Does it mean that in order to observe the lack of unitarity, we need to build an apparatus which is itself a microstate of a black hole? Or is it somewhere in between the two? Clearly, low energy experiments can't probe this.
No, I'm not sure. And I'm not even sure it's different from the nuclear case. I don't know. Maybe someone can jump in and help me out here, but I'm not sure it's different. Couldn't you say that that nuclei actually are a random theory, but there are super selection sectors, and when we went out and started doing experiments, we chose our super selection sector and
with the nuclear we do a little better because we can UV complete them in a unitary framework, and we have QCD, and we may be happy with that picture of nuclei, even if there could be another one. If this was the 50s,
right? But did we decohere ourselves into that? By
sorry, I think I might maybe be qualified to jump in, but the embarrassing thing is that as I actually sent to you, Tom, I was in a faculty meeting, so I actually missed most of what was being said in your talk before. But this question, so Dio, what was exactly your analogy to nuclear physics?
It was Tom's analogy.
Well, I'll summarize the discussion, Julian. So I just said that maybe it's similar to nuclear physics in that random matrix theory gets stuff right, but it's not a random matrix theory, of course. And then Dio was asking me, I guess you're asking me, how do we decide in principle which situation we're in? Like if we can build Planck scale apparatus, or if we can manipulate black hole microstates, then is there a way to tell whether we're in the ensemble average situation or the quantum mechanics interpretation? Because Julian, I've sort of phrased the discussion as arguing that there are these many wormholes, but we often have two interpretations: the
Yes.
ensemble average interpretation and the it's just coarse graining and low energies interpretation. And yeah, so that was the context.
Yes, I mean, I think that in the case where random matrix theory comes out as some sort of approximation, which is the case that we believe to be true for nuclear physics, then there are subtle deviations from actually random matrix physics that are apparent. That they become apparent, I guess, at earlier timescales. But to rule out some sort of generic interpretation in terms of some averaging, I think that is, of course, that's the crux of the question. That's something that for low energy probes might be difficult to do in principle, I think. But you see, of course, there will be discussion on ADS, and actually one of the ideas will be to discuss those sorts of questions. So we might have more time to talk about it then.
Good.
But you see, I mean, in nuclear physics, the story is known because we know the UV theory. I think this is also what Tom said. And there is a framework in which we can show how that UV theory leads to sort of random matrix predictions, and also how these random matrix predictions become less and less good as you move forward in time. And there I could tell you a long story of how it works. But if we don't know in principle that the underlying theory doesn't involve at least a little bit of ensemble averaging, even that we don't know, right? Then it will be a more subtle question even.
I'll tell you my bias. I might as well tell you my bias, which is that I feel that we should just obviously take the quantum mechanics interpretation until forced otherwise, because
yeah, I like that, but I also like to say the answer is I have no need for that hypothesis. Right. Which someone else said before, who was, of course.
We're all so conservative.
No, we're radical. We don't believe that there's a creator. Well, sorry, we don't need the assumption.
Okay, so technically we have 5 minutes, but I don't know, should I do bracket wormholes or should we discuss and conclude? Bracket wormhole?
So how much time do you need for that?
Well, I can do it in 5. If we talk, it'll be 10.
Maybe, yeah, we can go a bit over, let's say another 10 minutes, but then it would be good to break for 15 minutes to give people time
Sounds
to
good.
relax. Yeah.
Okay, I'll put a strict cutoff at 10 more minutes.
Okay.
So wormhole number 4 is the bracket wormhole. And I'm going to explain this in a slightly non-traditional way. So since we've already discussed the replica wormhole, I'm going to reinterpret it as a bracket wormhole. Okay, so in this calculation of the replica wormhole, let's just reinterpret the path integral on one copy of the black hole as a pure state in doubled Hilbert space. Okay, so if we do the path integral, with a cut like this, which was the bridge of the replica wormhole, then that's just a pure state in the doubled space where one copy of the Hilbert space is associated to the top here and the other is associated to the bottom. Or we can just think of it as fattening it out a little, and we have a quantum state on this mouth. Okay, so with this interpretation, now the replica wormhole is contributing to an overlap of to calculating the norm of this quantum state rho sub r. Okay, so the top part of this is preparing the bra, and the bottom part is the ket. And gluing them together along the cut is just the usual gluing of the path integral to calculate this norm. But when you interpret it this way, this seems like a pretty strange thing to include. The wormhole seems a little strange because in this picture, with Euclidean time going to the right, it seems as if the path integral goes back in time to change the state that you prepared, deciding on what you decide to calculate. I think this always happens in Euclidean gravity. It's not that exotic, but it's a little strange. And there are other Brockett wormholes distinct from the replica wormholes. And some of them might be relevant in cosmology. So that's the last thing that I want to mention. So the first one we can talk about is related to de Sitter space. So when we calculate so let's take the no boundary wave function of de Sitter and calculate its overlap. So this is just the usual Euclidean partition function of de Sitter space, which is a path integral on a sphere. Think of the bottom of the sphere as preparing the bra and the top of the sphere as the ket. Well, why not include higher topologies like the one here, where you have a bra-ket wormhole joining the bra and the ket like this? If we're just thinking of this as a Euclidean gravity calculation, I don't see any reason to exclude this. We probably have to include it in our path integral. Now this one, by this one I mean this de Sitter calculation, is not a saddle. At least I don't know of any way of finding saddles that look like this. And it's unknown whether this is important for anything. We don't know whether this particular Brockett topology that I've drawn has any meaning to it, something we can extract reliably. I'll just mention as an aside that stability matters here. You have to worry about when you find these wormholes, you have to, especially if you're imposing constraints, then you really have to check stability. And so this is a hard problem about doing a path integral coupled to quantum fields. And I don't have anything else to say about it. But there are wormholes, wormhole saddles, Brockett wormhole saddles, involving crunching universes. So that's my wormhole. That's going to be our wormhole number 4. Here's what they look like. So we're going to do a path integral of this form. So what we're doing is we're defining a quantum state by doing a Euclidean path integral. And we choose to put gravity on part of the Euclidean space with a negative cosmological constant. That's with some, looking forward, it's going to make sense for crunching universes. So I want this to end up being a crunching FRW, and that's why I've turned on the negative CC. So there's a negative cosmological constant down here, but up here we just have Minkowski space and no dynamical gravity. Now let's calculate the overlap. Or I guess the way I've drawn it, I've drawn it as a calculation of the density matrix. You can think of this as a calculation of the overlap if you fill in this region A. But the density matrix corresponding to that state that we've just described is a path integral on this manifold with a cut. Okay, so there's gravity up here, there's gravity down here, but there's no gravity inside that strip. And well, there's another contribution, which is the Brockett wormhole, which is the second term drawn here, where you thought you were doing a path integral on a half space, or 2 copies of the half space that were disconnected. But you don't get to decide what gravity wants to do. You just have to do the path integral with some boundary conditions. And the path integral might decide to do this. This is this is another contribution to the path interval, and I see no reason not to include it. And in particular, it's a saddle in this. If we pick our parameters, if we pick our parameters appropriately. So what this saddle looks like is in the non-gravitating region, it's obviously just flat. But the saddle point contribution to the gravitating region is a Euclidean crunching FRW universe with the metric that I've written here. So if we go to Lorentzian signature, that becomes a cosine, and you see the metric of a crunching FRW. But I'm drawing these pictures. We're doing this in Euclidean, so it's a cosh. Now, depending on what observable you calculate, either one of these saddles might dominate your calculation. And that's a little strange because they're very different. They look like very different quantum states. In the first one, the unwrapped saddle, matter fields are in the ground state. But in this Brockett wormhole, the matter fields are experiencing this as living on a cylinder. So the matter fields are going to be thermal. And that's exactly the energy density that's supporting the FRW universe, these thermal matter fields. Okay, so now I'm going to conclude. So I'll just leave it with the question I asked at the beginning. How much does gravity, low energy gravity, know about the UV? Well, it seems to be a lot more than we thought. And this is the crux of the question. So let me stop there. Thank you.
Thank you very much, Tom. So can I have another 5 minutes for questions, I think, but then we should really break to give time for people to relax before the next talk. So any questions, please raise hand. Yeah, go ahead, Alexander.
Thanks for the nice talk, Tom. I just wanted to make a comment about the thing that you mentioned at some point during the talk, that maybe low energy gravity knows everything universal that there is to know. I think there's some arguments against that it maybe knows even more. And if you take these wormholes seriously, many of the wormholes are supported by matter fields, or you can turn on sources for all kinds of operators. And the operators that you're allowed to turn on, that depends very much on the theory at hand. And then there's a second issue, which is the issue of stability. And again, stability depends on what low energy fields you have. So
I guess when I say universal, I want to include that in the meaning of universal. So
okay, I see.
It's like universality. There's a universality class, and I think we should include the set of low energy fields in the definition of the universality class.
I see. You mean, yeah,
I totally
okay,
agree with what you're saying.
Yeah. So then I think I agree then. Everything universal captured by that low energy theory, no matter what the UV completion is.
Yeah. Now I'm afraid that answer might be tautological, but I don't know. I don't have a better answer to offer.
Thanks.
Tarek.
Hey Tom, thanks for the talk. Yeah, I'm somewhat worried that about like what you were just mentioning, because also it seems like whether or not you include these replica wormholes could be a matter of what your theory allows. Like, for example, your measure could just cancel them out, or there could be gauge equivalences between states such that you might think semi-classically that such a thing should be counted, but then its effect is nothing. So how do you like tell without knowing, like without having actual toy models, which one is the case?
Yeah, I totally agree with your point. But again, my bias is that our goal as low energy observers isn't necessarily to, like, maybe we're not supposed to be able to answer that. And we should just say, well, yes, obviously we do include them because of quantum mechanics. I think maybe our goal as low energy observers is to show that it's consistent. but maybe we can't answer for certain what's happening in the UV.
Any more questions? Still have some time.
I can ask a question. Sorry, I can't raise my hand.
Yeah, go ahead.
Hi, Tom. Do you have any comment about these claims that the story of having regions where gravity switched on, switched off only makes sense in massive gravity?
Yes, let me make a comment. So at a technical level, I agree with everything that they're saying. It's true that when you do something like this, you give the graviton some mass, but I'm not sure. I don't think it's a problem. In fact, it may be a feature rather than a bug. And in fact, the same people who wrote the papers saying that it's only in massive gravity showed that that's a good thing. Because it resolves some problems that you would have with making sense of islands otherwise, because there's issues that you need to break some you need to break some of the diff constraints in order to resolve these problems, and it's the slight mass of the graviton that allows you to do that. So I think maybe that's just okay. And now where we differ maybe is that I think they might say, well, this is all well and good in a theory with massive graviton, but who cares about a theory with massive graviton? That's not the theory that I care about. And maybe everything is completely different in a theory with a massless graviton. And that's where I disagree. You know, if we study electromagnetism inside a waveguide, I think we're still studying electromagnetism. Maybe our apparatus is a waveguide, and then the photon is gapped. But I don't know that it's a problem. If
their statement seems to be fairly explicitly that, for example, the page curve fails to actually turn back if you take the massless limit. So if you make your waveguide infinitely big again, then you're back with the same problems, is what they would say.
No, they would say the page curve is 0.
Yeah, but I think my response to that is that, well, that's not the page curve. To talk about the page curve, you have to be able to separate the radiation from the geometric degrees of freedom. That's what was always meant by the page curve. It was not the full entropy of quantum gravity. That's not the page curve. The page curve is the entropy of the radiation alone. And in other words,
how would you separate the two then if you don't have this slight mass, I guess?
Well, I think the way to separate them is to introduce the boundary condition that produces a slight mass. I think that is the way to separate them, and that is what we should mean by the page curve.
Mm-hmm.
There could be other ways
otherwise
as well.
Otherwise we can't even talk, as they've shown, otherwise we can't even talk about the page curve or make the separation that's necessary to talk about the page curve.
But Tom, there could be other ways as well, right? You don't need to necessarily like couple the CFT to a bath. You could form a small black hole in ADS, and you know, then that would form a black hole for some time and evaporate. And there you presumably there's a way to define some reduced observables or some reduced algebra of observables that, you know, would follow something like a page curve, even though maybe it can't be defined very sharply.
Yeah, I agree. There might be other ways of making a page curve. Yeah.
Like coupling to a bath is one way, but would you say that it's fundamental that you need to do it that way?
Well, for black hole in flat space, it's hard for me to imagine how else to do it other than to treat the radiation as a separate system.
Yeah, I agree.
I don't know. I'm not. Maybe it can be done, but I don't know. I don't know any other way to think about. I don't know any other way to even talk about a page curve.
I'm slightly confused because once we have massive gravity, it's hard to build a consistent theory, no? It requires UV completion at fairly low energy scales, has these extra degrees of freedom. If you don't tune operators properly, there's even ghosts. So maybe, is it, yeah. Don't you have to like, in fact, as far as I know, people don't even know if there are black hole solutions in massive gravity. So.
Yeah, I have two comments about that. One is that I agree that it's not really clear that this is allowed, the boundary condition that's used to make this separation. And I think that's an important problem, at least an important technical problem. I don't know if it's an important conceptual problem, but it's at least an important technical problem. The other comment is that I don't think we have to make the separation until the black hole is gone. Okay, so it's not that there was a massive graviton all along. It's that we had a black hole in ordinary gravity. It did all the usual things that black holes do. It evaporated. The black hole's been gone for 1 million years, and then we defined some region out near infinity where now we have to make this separation. But we can do that only once the black hole is gone and we've decided to do something with to measure something with the radiation. So I don't think it can. I agree that we don't exactly know how to do that because of diff constraints and so on, but I don't see a problem with it affecting the evolution of the black hole itself.
I see. Thanks.